Welcome back to the time series tutorial. We are on part 1, fundamentals, and we're talking about subpart 1.3, linear forecasting. So one of the favorite jokes, prediction is difficult, especially of the future, by Niels Bohr. So the problem is the one we mentioned at the beginning. Given a time series, let's say temperatures over the past 10 days, forecast what will happen on the 11th day. And the summary recipe is that we could use for linear forecasting, we could use the autoregressive methodology, also known as Box-Jenkins methodology, which is part of the ARIMA, autoregressive integrated moving average methodology. This is related to Holt winters and also to Kalman filter special cases. So let's see the first part, autoregression and least squares. Remember, the problem is forecast the 11th day. And statistics textbooks say that the first thing to do is to remove trends. If the temperatures go up, we should remove the trend. And the second step is to spot and remove periodicities, seasonally adjusted, as the meteorologists say. Then the brilliant idea behind the Box-Jenkins methodology is to try to express the temperature of tomorrow as a linear combination of temperatures of the past. The user has to choose a window of W, let's say W is 7 days. And then the autoregression methodology will find 7 coefficients, A1, A2, A7, so that the weighted sum predicts the future as best as possible. Let's go back to standard regression before we go to autoregression. This is statistics, introduction to statistics. Suppose we have 2 variables, patients with 2 variables, body weight and body height. For all the patients, we know the body weight. For all except the last, we know the body height. And the question is, how can we guess the body height of the last patient? The idea is to assume linear correlation between body height, body weight. Using statistical terminology, what we know is the independent variable in blue. What we want to guess is the dependent variable in red. And linear regression says we should fit a line on those points. Every point is a patient with body height, body weight. And then when we want to guess how tall should the last patient be, we bring a line, a vertical line from the weight, 25 units of weight, and then we bring a horizontal line until we hit the vertical axis. So this up and left motion, we'll see it again and again. This is standard for forecasting, for guessing the value, for regression. Okay, this is standard. This is, we all learned about it. What happens if we have a time series? Suppose we have temperatures as a function of time or number of packets in a computer network as a function of time. We want to figure out, we know everything up to now, and we want to guess what will happen in the next time tick. So clearly, this is the dependent variable that we want to guess. What is the independent variable or variables? And here is the genius of Box and Jenkins. They say use the same time series lagged by 1. So this is the methodology with lag 1, just the window is only 1, just for illustration, but as we'll see later, it can work with any window. So now the idea is very clear. We have a time series which is delayed by 1. Everybody except for the first pair is matched up nicely, except for the first and the last pair. So we are back to the original problem. Every time tick corresponds to a pair of successive time ticks. The horizontal axis is the value before, the vertical axis is the value after. Again, we fit a line, and then we do the up and left trick. So we guess that if we had 25 packets the time tick before, we should have 55 packets in the next time tick. So the dependent variable is the number of packets sent at time t, and the independent variable is the number of packets sent at time t minus 1. Excellent. This works very nicely. There are a lot of details. This is just the tip of the iceberg, right? And among the most interesting details are how to handle windows of higher size, more than 1, and how to do it incrementally. So let's see the first part. So how could we make it work when we want to have a window of 2, when we suspect that the temperature tomorrow depends on the temperature today and the temperature the day before? This is geometrically, this is very easy. Now we'll have, instead of points in two-dimensional space, we'll have points in three-dimensional space. We fit a plane for the day's temperatures tomorrow, today, and yesterday. And then if we want to guess what will happen tomorrow, we do the same trick, move upwards and then left. And this is the guess. How can we do it mathematically, in addition to geometrically? Notice that this is deep dive. This is details that we don't need to fully understand. The idea is that the problem becomes an over-constrained problem with a lot of equations, as many as historical data we have, and very few unknowns, just the weights of the window we want. If we want a window of 7, we have 7 unknowns. If we want a window of 1, it's just 1 unknown. So the problem is heavily over-constrained, but we know how to solve it. It's a very well understood problem. Let me continue the deep dive and show how we could turn the forecasting problem into a matrix algebra problem, right? So suppose we decide on a window of 1, 2, 3, 4, 5, right? So we have the first 5 days and their temperatures. They form the first equation. The value we want to guess is the green value. Let's call it y1. It's the temperature of the next day, the 6th day. And this is our first equation. We slide the window by 1, the next 5 days, and the next day, the day after that, form the next equation, and so on and so forth. So we'll have as many equations as time ticks, -5, and as many unknowns as the window we want, 5 in this example. How do we solve it? This is a closed formula. This portion, the pink portion, is the Moore-Penrose pseudo-inverse of the X matrix we showed before. The bottom line is that this is an extremely well understood problem. We give it for homework in classes, and this is the solution. There are many more details. Can we estimate the 7 parameters we want, or the 5 parameters of the vector A, incrementally? And it turns out that we can. There is the brilliant method of least squares. The paper by Yi and the rest of us describes exactly this method from textbooks. And the idea, the high-level idea, is that if we have window of one dependent variable and one independent variable, then we can fit a line to our historical data, the blue line. If a new point comes in, then we don't need to refit to solve the huge big Moore-Penrose pseudo-inverse problem from scratch. We can just update some small equations, a W by W matrix. In our case, this will be 1 by 1 scalar with a new point, and we can compute the new slope very quickly. So this is the recursive least squares, and strongly recommended if you're working on streaming data. How can we handle co-evolving more than one time series? Remember, one of the problems we mentioned in the beginning is, what if we have 3 time series? Number of packets sent, number of packets lost, number of packets repeated. What will happen in the 11th day? Let's say for the green packets, for the repeated packets. The problem is mathematically identical to regression. Actually, it is called vector ARIMA. But the problem is exactly the same. We want to guess how many repeated packets we'll have at time t. Based on a window, pick a window size, W, let's say, equals 5. Based on a window of 5 for the packets sent, packets lost, and packets repeated. The mathematics are exactly the same as before, Moore-Penrose pseudo-inverse, and we can solve the problem. So the conclusion is that linear autoregression is very well understood, and the autoregression with window 1, 2, and 3 is usually gives good results, and this methodology is the basis for more complicated and even more successful methods like Holt, Winters, and Kalman that we won't mention, but we'll give pointers. Here are the citations. The book, the classic book by George and Jenkins in its 3rd edition. Brockwell is an even more advanced book. For Kalman filters, we had a tutorial in 2010. You're welcome to take a look at the foils. They're still on the web. And we are ready for part 1.4, how to do nonlinear forecasting. So first we'll see the problem, then the main idea, then details, experiments, and Volterra-Lotka equations and conclusions. So the problem again is, given a time series, figure out what will happen next. But the footnote is that this is a tricky time sequence. This is chaotic or coming from a nonlinear difference or differential equation. In that case, linear methods will not work, but the method that gives good results is the so-called delayed coordinate embedding method, which uses lag plots and then similarity search, which is the reason we spend so much time on similarity search in the beginning. So here is a time series. Notice that they are not really periodicities. It seems to be periodic, but not really. There is there seem to be spikes, but the spikes disappear. Here the spikes disappear again. After 6 periods, there is one disappearance. So it's a very strange time series. And actually, this time series came from this difference equation, which is called the logistics parabola, which was proposed by Sir Robert May, one of the main figures in population ecology, who proposed this model to model the population of flies and insects. So instead of flies, we'll have the ladybird, which is much prettier than a fly. So this equation makes a lot of sense. It says that the population of flies in the next time tick, in the next year, depends on the population of flies this year, times the reproductive rate, how many eggs flies tend to lay. But there is a throttling factor, right? If there are too many flies, then the reproductive ability goes down because there is not enough food to share, there's not enough oxygen in the laboratory room of Professor May, and so on and so forth. Technically, X is not a count, is the ratio, the fraction of the number of flies versus the carrying capacity, the absolute maximum number of flies we could fit in a room, right? But the equation makes sense. Things propagate with a reproductive rate unless this reproductive rate gets slowing down because of the population approaching huge capacity. This is the equation that we use to generate this synthetic sequence. And if we plot xt as a function of xt plus 1 as a function of t, we'll clearly get a parabola which crosses with 0 crossings at 0 and at 1, right? 0 and 1. Okay, this makes a lot of sense. This models real populations reasonably well. Actually, it's a very, very successful equation. It also models virus propagation epidemiology for the specific type of SI, susceptible infected. This is a virus that never goes away. People never get healed, never heal and never recover. So it's a virus from hell. But this is also very, very similar to the Bass equation for market penetration. So if there is a product, let's say this marker, right? If I tell you that, hey, this is a nice marker and a fraction of you go and buy this marker, this is exactly how the marker will penetrate the market. According to a very similar equation to the logistics parabola. And as we'll see later, this logistic parabola is a special case of the so-called Lotka-Volterra equations, which model not only one type of species, but multiple types of species which are cooperating or prey-predator relationship or some other relationships. So it's a very interesting and very useful equation. So how would we forecast? In the previous section, we say, okay, if we have a time series, let's use autoregression. Let's see why autoregression is not a good tool here. Because let's say if we have autoregression of window 1, then this will be what we are doing is we're trying to fit an equation of this form. No matter what the intercept and the slope, this will never match the parabola. We're trying to fit a square peg in a circle hole, right? So it will never fit. What should we do? If we know exactly the shape of the parabola, then what we can do is we can do the up and left motion. What is the population of flies this year? Go up, hit the parabola, go left. These are guess for next year. If we don't know the parabola, the exact details of the parabola, but we have a lot of historic data, how could we go about it? And that was the idea behind Tim Zauer's method. Says, let's assume that we have a window of 1 is enough, so lag 1, and let's assume that 4 nearest neighbors are enough. So let's So we have a lot of historical data, which are these stars. We don't know, and actually we don't even care if they're on a parabola or hyperbola or anything else, right? But what we do is we figure out what is the value for today, the population of flies for today, for this year. Then we look for the 4 nearest neighbors on this horizontal axis. From those 4 nearest neighbors, we do the up and left motion. We go up and see what happened after in those 4 cases. We figure out all these points, and then we interpolate among the four forecasts. Something like that. So we get the green point. So this is the high-level idea behind the delayed coordinate embedding method. There are a few details to discuss. How would we interpolate between the 4 nearest neighbors? And one obvious answer is the average. A second answer is the weighted average, weighted according to how far away you are from the red point. The winning answer, which actually Tim Zauer used and won first place in the time series forecasting competition in 93, was to get the 4 nearest neighbors, figure out the points in their appropriate dimensional space, fit a hyperplane using singular value decomposition, and then do the upward and left motion. So there are a few details. What is the right value of k to use for nearest neighbors, and how much should be the lag? In this example, we had the lag of 1, xt plus 1 versus xt, and number of neighbors was 4. What is the recommended number of neighbors? There are no hard rules. Tim Zauer said that the number of neighbors should be more than 1 and less than, but not too huge, because otherwise we average over the whole population. And in his experiments, a lag of 16 gave good results. There are a lot of papers on how to choose the appropriate lag using mutual information and other complicated techniques. We won't go into detail. So how does this work at all? It seems to make sense, but is there a theory behind it? And now we're doing deep dive, right? The answer is there is a theory, and actually there is the Takens theorem, which says that if you have a long enough history of whatever quantity you want to measure, then you can do good forecasting even if there are other unobserved variables. So let me give you an example. So suppose we want to forecast the population of lynx that we have been going after all along. And suppose that the lynx interact with snow hare, because that's a prey-predator relationship, right? So, and we can assume that they interact with Lotka-Volterra equations, which make a lot of sense and which we'll show in more detail later. So what this says is that here, the increment in the hare population depends on the hare now and the reproductive rate, how many rabbits are being generated by a pair of rabbits. But this is reduced by how many rabbits encounter a predator, lynx, and the probability that the rabbit will not escape, will not evade the predator, right? Similarly, the predators, they will get a lot of calories. Every time a predator finds a rabbit and eats it, then it gets calories, and then it has the capability to generate offspring. If there's no hare at all, if there are no rabbits at all, then the predators will decrease in this model with exponential decay, right? So if we know both the number of predators and the number of preys, we can figure out exactly what will happen next. What if we only know the number of predators? It turns out that we don't need to know the number of preys if we have a long enough history of the predators. This is the idea behind Takens theorem. And actually notice how this is called the state space. So this is the number of rabbits and this is the number of lynx. Notice that if there are a lot of rabbits, the population of lynx will go up, which will make the population of rabbits to go down because they are devoured by the lynx, which will make the population of lynx go down because there's not enough food, which will give an opportunity to rabbits to start multiplying because there are no predators, and the cycle will repeat. This is called the limit cycle in dynamical systems. So this is, according to this model, and this is from Wikipedia, according to this model we saw before, the population of predators will have spikes, as we saw for the real data. The population of prey will also have spikes, the green shape, right? And this will be the limit cycle. Okay, it's a triangle, but technically it's a limit cycle. And Tuckin's theorem says that if there is a limit cycle between prey and predators, we will also have a limit cycle between predators at time t and predators at time t minus 1. Therefore, whatever forecast we do with full information of lynx and rabbits, we can also do with enough information about lynx alone. This is the idea behind Tuckin's theorem. The bottom line is that the delayed coordinate embedding method has theoretical underpinnings, and this is the reason it is successful. So, Lotka-Volterra equations, we'll see them again later because they help with gray box modeling. Let's see how well this method works on synthetic and real data experiments. So, we tried it first on synthetic data generated by exactly this equation, the logistics parabola. And it turns out that if we do delayed coordinate embedding, autoregression will fail. But with delayed coordinate embedding, we get, this is what we knew, the red stuff. This is what we forecasted, the green stuff. And if we superimpose the green we forecasted with actual, we'll see that it matches very well, at least for the first few time ticks. After a while, as we'll see very quickly, nobody can do good forecasting. The second data set is the famous equation by Lorentz, synthetic data set, which try to model the weather. So X is wind velocity, Y is pressure, Z is humidity, or something like that. So the differential equations that model convection, model the weather, look like that. So this is the value of X, if I remember correctly, as a function of time for some choice of parameter, for a carefully chosen set of parameters A, B, and C. Notice that it's not really periodic. There is a period, but it keeps on growing, and then things go crazy. And then it sort of looks periodic again, but then drops back into the previous type of periodicity. So this is tricky. And actually what happens, there is a very nice history here. People in the 50s, famous mathematicians in the 50s, they said, okay, here are the equations of the weather, so we can forecast the weather. So let's talk about how to control the weather. And Lorentz threw a bombshell saying that even if you know the equations, you cannot really forecast the weather because you cannot really forecast any nonlinear system because of the butterfly effect. If your system has a limit cycle, then everything is good. If you're here, then you'll go on the red triangle. If you're a little bit off, you will go on the blue triangle cycle, right? But if you have a strange attractor, as it happens in this case, a small deviation, if you start from here as opposed to here, after a few time steps, you will be in a completely different trajectory. And this is the so-called butterfly effect, which postulates that if there is a butterfly in China flapping its wings, it will affect how a hurricane in Texas a year later goes through the country. So the shocking discovery is that for nonlinear systems, there is a possibility that even if we know the differential equations that govern the system, we cannot do long-term forecasting, the butterfly effect, right? So with synthetic data generated by the previous equations, we try to do the delayed coordinate embedding method. And yes, it does good forecasting up to several time ticks. And then, of course, the butterfly effect kicks in and nobody can do good forecasting. So let's go back, let's open a parenthesis. This is what we said so far is black box modeling. We don't know anything. We collect historical data and we try to do forecasting. What happens if we believe that the Lotka-Volterra equations is true? How can we use it to do better forecasting? So these equations model prey-predator relationships, as we mentioned before, lynx and rabbits. They also can model competing animals like rabbits and goats. This is not a prey-predator relationship, but they compete for grass, for example, and resources. The same is competing products, market penetration, people, stocks versus bonds. They all both try to feed on the available income of citizens, and there is a competition. If we have only one species, then this is the bus model, how quickly a product will penetrate the market. And similarly, if we have only one type of virus, how quickly a virus will cover a population, and so on and so forth. So these are extremely useful equations for many settings. The gray box modeling, the high-level idea is as follows. If we believe these equations, and if we have historical data for age, for the hair and the lynx, then what we can do is look at the historical data. We can try to estimate these parameters, the reproductive parameter for rabbits, the reproductive, the rate of death, the decay for predators lacking food, and so on and so forth. And this was exactly the idea behind the paper with Professor Yasuko Matsubara and Yasushi Sakurai, where the code is in this website, and the paper appeared a few years ago in www. So the goal was to guess how competing products will evolve. So these are 4 gaming consoles, Xbox, PlayStation, and so on. The vertical axis is the number of Google queries normalized to 1. And we see that Xbox starts high and then fluctuates and so on. The spikes, as you can imagine, are during Christmas. And to my surprise, there are also little spikes in May and more little spikes in September, which is surprising given that school starts. So the goal is, if we believe that there are Volterra-Lotka equations among these competing products, can we guess how they will evolve in the future? So the situation that we conjecture, that this paper conjectures, is that all these consoles, they need resources. The resources are the available income, the disposable income from children, teens, and adults, right? And this is exactly the same, mathematically, it's exactly the same situation as species in an ecosystem fighting for resources. So squirrel monkeys, they need fruits at a high degree, and they can also survive on nuts, but not their first preference. The macaws, they survive explicitly on nuts, and we want to figure out how the population of these species will evolve. So that's exactly the problem formulation. And let's dive a little bit deeper on the Lotka-Volterra equations, which say that the population of species I, suppose we have D species. In our example, we had 4 consoles, game consoles, right? Suppose we have D species, so the population of lynx for next year will depend on the population on lynx for this year, and also on the reproductive rate of lynx, how many baby lynx are generated in a couple, throttled down by the influence, by how much harm other species do. So Aij is the harm factor of species J, rabbits, to species I, lynx. In this setting, the harm factor is actually negative, right? The more rabbits there are, the happier the lynx, right? But other things might be positive. If there are humans, for example, humans is one species, humans will have harmful effect on the lynx, right? Lynx themselves, the factor I sub I, are actually harming each other, because the more lynx are available, the less resources are for a given specific lynx. And actually, this formulation can model all types of interrelationships between species. So if both Aij and Aji are both negative, this is symbiosis, right? This is 2 species that one helps the other, like sharkfish and pilotfish. If they're both positive, this means that they're competing. If one is positive, the other is negative, it means that it's a prey-predator relationship. If both are 0, this means that the species don't care about each other. It's like polar bears and alligators, right? There's nothing, they don't have anything in common. The Ki is the carrying capacity. What is the maximum number of links we could possibly fit in this ecosystem if we pack it with links from coast to coast? So these equations are the Lotka-Volterra equations, and these are the ones that Professor Matsubara tried to fit on these time series. After the fitting and using seasonality, she was able to compute the parameters, fit the parameters for the 2/3 of the experiment, and then forecast the last third, and the fitting was made a lot of sense, was close to reality. And as we said, the open source code is here in Python, if I remember correctly. So this closes the parenthesis on gray box modeling, and the conclusions are that if we have chaotic nonlinear systems and we are sure that autoregression will not lead anywhere, then we can use lag plots and similarity search, the name of the method of delayed coordinate embedding. This is the paper by Tim Zauer, the one that won the competition, actually tied in first place with a neural network of the 90s, which was not a deep network, of course, they didn't exist yet. But it was a neural network with one hidden layer and sigmoid functions, if I remember correctly. The paper by Takens, the collection paper by Weigand and Gershenfeld, and we're ready to cover 0.1.5, the tensors. So tensors will help us model time-evolving graphs. So if we have a graph, who bought what, this can be modeled as a matrix, as a graph. What happens if we have time-evolving graphs? For example, not only we know who bought what, but we also have the timestamp. And notice that this person, the gentleman with the blonde hair, bought this product 2 times, 10 p.m. and 11 p.m., right? So when we have such a time-evolving graph, what are the models and what are the tools we should use? And the answer is, in that case, tensors is a powerful, well-understood tool. Let's see some examples. A tensor is actually a generalization of a matrix. So suppose we have the rows are authors that published in www17, and the columns of this matrix are keywords, and the entry is how many times author John used the term data in his papers, right? How many times author Mary used the term data in her papers, and so on. And that was www17. www18, we do the same thing, and 0pad, if somebody didn't publish or didn't use the word data, we filled it with a blank, with a 0. And the same for 19. So now instead of having a matrix, we have a stack of matrices. And this is exactly called the tensor. The axis of the tensor are called modes or aspects. So in this toy example, the first mode is the terms, the second mode is the humans, the authors, and the third mode is the time. And then this can help us do forecasting. Because if we try to do straightforward forecasting, suppose, as we'll see later, we have a real data set of who calls whom and when. So in this case, if we want to do forecasting, we have 4 million people calling 4 other million people. If we try to do forecasting on a pair basis, a caller-collie basis, then we would need 4 million square autoregressive models. So this will be prohibitive, plus it will be extremely wasteful. Most of these pairs don't call each other at all, 0, 0, 0 all along, right? So forecasting on a specific level, on an individual level is a bad idea. It won't work, it won't scale. Tensors will help us solve this problem. So the tool that we will use is the so-called parafac, parallel factor decomposition. And it's a generalization of singular value decomposition. Blue background means that we have seen this slide before, and this was exactly what we did to find hidden variables in stock prices. So remember, the rows were stock prices, the columns were timestamps. If we feed in this array into the Python package and ask for rank 2 decomposition, we'll get the 2 vectors, the projections of our stocks in a 2-dimensional space, and we'll get the 2 behaviors, the 2 hidden variables, the global growth of the economy and the internet boom here at 2000, 2001. An even better interpretation of singular value decomposition is by a matrix of who buys what. So suppose we have a store and we are selling, we have so many customers and we have so many products. And suppose in this fictitious store, all these people buy all these products, and all these people, all the blue people buy all the blue products, and so on and so forth. And there's no intersection between the people in the green concept, green hidden variable, and the people in the blue hidden variable and the people in the pink hidden variable, right? So let's assume that the green blob corresponds to people who are fashion aware, and the products are fashionable shoes. The blue blob, the blue hidden variable, corresponds to Apple fans who will buy anything that, any i product, iPad, iPhone, anything, iMac. And the third corresponds to affluent people who buy jewelry and so on. So the singular value decomposition in this case, if we ask for rank 3 decomposition, will give 3 pairs of vectors, the U1, V1, which will correspond to the first concept. Correspond means that this vector will have zeros almost everywhere except for the people who like shoes, who are fashion aware. And this vector will have zeros everywhere except for the place that correspond to fashion products, shoes and so on. The same for the blue blob, Apple fans and Apple products, affluent people and jewelry products, right? So this is what singular value decomposition does. If we have a tensor, and if our tensor has very nice blocks, all these people bought all these products during all these timestamps, right? And all these people bought all these products during those timestamps and so on, then the parafact decomposition will give us, of rank 3, will give us triplets of vectors. And these will be indicator vectors, more or less indicator vectors for which person participates in the first concept, shoes, which product participates in the first concept, and which timestamps participate in the first project. So suppose that fashion-aware people shop during the weekdays, Apple fans shop during the summer months, and because that's when there are big breaks or big discounts or whatever, and jewelry lovers buy stuff during the holidays, right? So this is the interpretation of the vectors that parafact generates. Now there's a big advantage, because if we want to do forecasting, we don't have to forecast how many times Smith will call Johnson or this person will buy shoes. We can do forecasting on the 3 major concepts, on the 3 hidden variables we have discovered, and then we can reverse engineer how the tensor will evolve. So we'll need only 3 models. In this toy example, only 3 forecasting models. We can use autoregression, we can use delayed coordinate embedding, whatever we want, but we need only 3 models, as opposed to 4 million square, which is completely out of the question. So we repeat again the observation that when we're able to find patterns, we can do forecasting, and this is exactly what parafact helps us do. It can spot hidden variables over customer, products, and time, or caller, callee, and time, as we'll see next, and so on. So let's see application of parafact on 3 settings: on a who calls whom network, on network traffic, who sends packets to whom, and on Facebook, who posts messages to whose wall. So for the first data set, that was real data from a European country, 4 million customers calling each other over 2 weeks. So the first, we did parafact analysis. The first triplet of vectors was not very interesting. Everybody was calling everybody else, and there was a weekly periodicity, not too many phone calls during the weekends. Okay, not surprising. The third or fourth triplet of vectors was very interesting. This is the vector. It has 4 million entries, hard to plot, but all of them are near 0 except 1. The second vector, which corresponds to receivers, again 4 million entries, all of them near 0 except for 5. And the third vector had 14 time ticks, and it was non-zero on only 4 days of activity. Everything else was silent. So this was very surprising, because we looked into the anonymized data, of course, and this person or institution or this originator of phone calls would call each other of the 5 receivers roughly 200 times a day for those 4 days. So we were not allowed to look into more details because of privacy issues, of course. So we gave a name, we call this pattern Godfather, we're calling this Godchildren for some reason. It may very well be very good reasons. It may be the head of a corporation giving instructions to the managers of the corporation for a big show that the corporation would like to do. So could be bad reasons, could be good reasons. But the point I want to make is that the parafactic composition was able to find this very interesting pattern without doing anything fancy. That's it. You load the matrix, you load the tensor, you press the button, and you look at the first few triplets, and this pattern showed up. With exactly the details are in this paper. The second data set is network traffic from also public data set. The main author here is Vangelis Papalexakis. Vangelis studied this data set. The tensor had no temporal mode in this example. It was only source destination, source IP, destination IP address, and port number. And one of the hidden variables had the following 3 vectors. There was only one source, only one destination, but they were communicating over multiple ports, which may be a port scanning attack or a peer-to-peer network, which is hopping across multiple ports to avoid detection. Either way, suspicious pattern. The third data set was Facebook. So now the tensor, the modes of the tensor was the wall owner. The second mode was the person who posted on this wall. And the third mode was timestamp. So this is one of the triplets, one of the hidden variables. So among the several thousands of customers, there was only one was the wall owner. The posters were several of them, but this activity happened on only one day, which is strange because other activities, they have 1 or 2 wall owners, a few posters, 1 or 2 posters, and the activity spans several days. So one possible explanation is that this is the birthday of the wall owner, and these posters posted on his or her wall to wish this person happy birthday. So the conclusion is that tensor analysis can find hidden variables, can find patterns when we have triplets or when we have source, destination, and timestamp. And as we said, patterns can help us spot anomalies if reality deviates from our expectation. And as we said, it extends SVD and matrix factorization to higher mode matrices, higher mode tensors. So here is the excellent survey by Tamara Kolda. We have a newer survey a few years ago with Nicholas Sidiropoulos and colleagues. And we are almost at the end of the part 1. The conclusions are, again, the problem of forecasting is closely related to pattern discovery, to lossy compression, to similarity searching in the past, and to anomaly and outlier detection. All the material we are covering is in this website, so I'll give you 2 seconds to figure out to download it or to write or snap a photograph. Feel free to stop the video if you are watching offline. And here is the 1-page summary of this presentation. For similarity search across time series, Euclidean distance is the prevailing distance. Time warping is good only if we have voice signals. If we want to spot periodicities, the digital signal processing provides valuable tools like the discrete Fourier transform and even better, the discrete wavelet transform. If we want to do linear forecasting, which is very successful for linear systems, the autoregressive methodology is the must try, and it's the stepping stone for more advanced methodologies like the Holt-Winters and Kalman filters. If we are sure that the system we are studying has non-linearities, then we have to resort to lag plots and the delayed coordinate embedding method, lag plots and similarity search and nearest neighbor search. We had a detour on the gray box modeling and the powerful Lotka-Volterra equations, which model virus propagation, market penetration, product competition, prey-predator relationships, and more. And finally, we saw tensors that they can spot patterns when we have co-evolving time sequences. The bumper sticker version of this whole presentation is that if we have a time series, as statistics books say, we should plot it. And as we saw in this presentation, it pays off to do the Fourier transform and the wavelet transform, looking for strange patterns. And this is the end of this presentation. Thank you very much. And let's go back again so that, and here is the place where you can download all this information.